Welcome to Everything Distributed. Today, I'm going to talk about one very simple idea in network science, and it's very related to COVID right now. It's on epidemics, and I'm going to talk about branch model. And the content is based on one subsection of this chapter 21 epidemics inside this great book, Networks, Crowds, and Market, Reasoning about a Highly Connected World. So it talks about the intersection of network science and algorithms. It's very easy to read and I highly recommend it. So what's epidemics? I think by now most of you should already understand it, but let me just remind you. So this is because of a contagious disease like flu, measles, or right now it's like COVID. And then why is it so special? Because that it will transmit from person to person, and then it's affecting the whole civilization. And then yeah, we are in a very tough year right now. And then there are multiple factors of this kind of epidemics. Then first, it will depend on the property of the virus, or like more formally called a pathogen. Like whether it's highly contagious, for example, COVID or measles is really, really high contagious. But like if you have other things, it's not as much. And then the length of its infectious period. So once you get it, how long will you remain contagious? And then why COVID-19 is so hard to stop is that this infectious period is really long, and then it's also less severe. And the more important factors that we kind of ignore because it's so subtle is the underlying network structure. So remember last time we talked about society, the interaction network, that's a network. And then in terms of epidemics, we care about the contact network. So that's why people are talking about contact tracing, because we have interaction network, and then if I contact you, if I got a virus, it's very likely that you will get it if we are very close. And then if we look at a CT scale, there's also travel, also work, and then this airline, and then of course a communication network that will also play a factor inside this epidemics, because how efficient you can communicate with each other, then that's also a factor. Then the pathogen and the network, they are actually highly correlated. So for example, like highly contagious disease, then you will have huge number of links in your underlying network, because this network means that the possible people that you might affect, or the possible people that you might the virus might jump or contagious from you to the other person. And then some of the diseases that only require close contact, or like sexually transmitted disease, the number of links is much, much less. So the network is not only a static, it really depends on what kind of disease, what kind of epidemics you are looking at. And here I'm going to introduce one very simple model to model the virus spread. It's called branch model or branch process. So the idea is that you have only one root, which is patient 0. Okay, so you have this person. And then the way that there are two important parameters, K and P. So the K and P, they are fixed. So like what K means is that you have one person, it always contact or interact with 3 people. So in this case, suppose K equal to 3. Okay. And then so effectively you are building a tree, because each person will interact with 3 people, so on and so forth. And then of course you will say that this is not very realistic. Yes, it's not, but like the beauty of a network science or beauty of theory in general is that it doesn't need to be very precise. It doesn't need to model exactly what we have in real world. It can still be very powerful. It can still teach something else that's important to us. For example, how to stop the spread. Okay. And then the next one is P. So the P idea is that for each of the branch here, you kind of flick a coin with probability P that's being a head. If it's a head, that means that, okay, this person 0, it will affect this person, say 1, let's say 2 and 3. And then suppose that this virus is not very contagious, so that you flip a coin here, it's a tail. You flip a coin here, it's a tail. That means that in the second time step, only one person has the virus. So the way to look at it is that t equal to 0, and then this is t equal to 1, so on and so forth. So that here and here is the definition of wave. So this t equal to 1 is the first wave. If you have a second level, it's that the second wave, so on and so forth. So this branch model, very simple. You have root, you have k, and then you have p. So k is the number of process or number of nodes that you are connected to, and p is a probability that you are successfully transmit the virus. Okay. And then the idea for termination is that you will reach a wave where that it fails to infect anyone. So suppose that 1, it flips the coin again and again, like 3 times, and nobody is affected, then it terminates. So this virus kind of dies. And then if you look at the bottom case, is that this person affected, this person affected, this person affected, but all the dotted line means that they are not affected, so it terminates. Okay. And then this bring out a very important concept. It's called R0. R0 is the expected number of a new cases caused by a single individual. Okay. So in this case, T patient 0, it affect one person, and then 1 doesn't affect anyone more. Okay. But that you need to take into account of all the possible virus spread. So remember, we have K and then we have P. So what would be the R0 in this branch model? R0 is actually means K times P, because that is kind of that you flip a coin for K times, then how many times that you are going to get ahead. And then if you know something about probability, it's exactly KP. Okay. So that's very simple. That tell you the basic reproduction number. And why is this so important is that under this branch model, you just look at R0. If R0 is less than 1, then you know that for sure, eventually the disease will die out after a finite number of waves, meaning that it cannot keep spreading. But if R0 greater than 1, strictly greater than 1, then with probability greater than 0, is that the disease will persist. It will keep affecting new people. It keeps spreading. So that's why that right now you hear the news is that we need to bring R0 down to 1. And then this very simple model tells you why we want to do that. Okay. And the underlying math is slightly more complicated, and I might talk about that in the future, but not today. And then I want to talk about that in terms of public health measures. Two very simple. One is that we want to isolate people, we want to quarantine people if they are affected, if they have a virus. And then of course we also want to have a better sanitary practice, or effectively we want to wear masks to stop the spread of virus, especially like COVID. It's highly contagious even by aerosol transmission. Okay. And then I want you to think about in terms of branch model, how do these two measures affect the K and P? So that would be your take-home exercise, And then while doing these two things, we'll bring down R0, and then we'll help us stop the spread of virus. So takeaway is that the branch model, and then how does this network science use the very simple model to give us this kind of big idea. You have R0 and we want to bring it down to 1, bring it down to less than 1. And then in terms of this, because epidemics is affecting everyone, and then we need to work together to really stop this. Okay. All right, that's all I want to talk about today. Thank you.